Hey everyone, here is RC Circuits Part 2. We are going to charge our capacitor now, which means that we're going to have an uncharged capacitor with a resistor and a battery now. There's no initial charge on the capacitor. Current will begin to flow when the switch is closed. And since there's no charge on the capacitor, what you could imagine is that an uncharged capacitor would act just like a wire. So as soon as that switch is closed, pretend there's just a wire there, and really you have one battery with one resistor, and your current would just be V over R. But as the current starts to build up and as the charge starts to build up on your two capacitors, you're going to have a voltage in the opposite direction. Let's say this is 12 volt battery. Eventually the capacitor will be charged to the same potential, except it's facing in the opposite direction. So it would try to force charges to go against what the battery is doing. So you'd actually have two batteries fighting each other, and what would happen is that eventually the current is going to go to zero. We're going to have maximum current right as we throw the switch, but after a long period of time, after a few time constants, you'll be at zero current. So that's the difference between charging and discharging. In charging, you don't even think about the capacitor until the capacitor has charged. Once it's charged, it's pretty much a roadblock for the rest of your circuit. So what this picture is showing is exactly what I was just talking about. Right now, the only way for current to flow around this circuit is from the battery through the resistor. It has to go to the capacitor and then back again. But again, since no charge flows across that capacitor, we don't need charges moving through a capacitor. All we're doing is piling positives on this end and depleting the positives on the other side, creating a negative plate. Again, it's going to fully charge, and when the capacitor fully charges, the circuit will shut down. But what would happen if we would shut that switch? If we would close the switch, current would flow out of the battery, it would pass through the resistor, and now it has a choice. Do I go across a wire, which has really no resistance, or do I go to a capacitor? And so what it would actually do is short circuit the capacitor and just be a resistor and a battery. So it'd be everything that we've known before, but as soon as that switch opens, then charges have to start piling up on the side, and we'll get the charging RC relationship that we're about to show. So here is our charging setup for an RC circuit. We've got the battery again, resistor, and capacitor. Remember, capacitor is initially uncharged, so at the beginning, Q equals 0. So in the beginning here, when we throw the switch, remember the capacitor is not really there, or at least the battery doesn't see it, and there's no charge on it, which means I've got maximum current. It's like you didn't even have a capacitor in your circuit and you just had a wire. But again, as the capacitor starts to charge, the battery will sense that the capacitor will shut down the entire circuit. So as the charge increases on the capacitor, the current is going to decrease. We're going to lose current and lose the flow of charge as time goes on. So let's do our loop roll. Let's go around the loop like we did last time, but this time we've got one extra thing to add into our setup. So we're going to set it up as 0, go across the battery and gain a positive EMF. I'm going to go across the resistor and lose IR in terms of voltage, and then I'm going to go across the capacitor. For the capacitor, you're also going to do a minus Q over C to find the voltage in the capacitor. The reason it's minus is because this side of the capacitor is going to be positive, while that side of the capacitor is going to be negative. And if that's the case, the loop is going against the way the capacitor is charging, so we're going to put energy into the capacitor. So we're going to lose voltage across there. So there's our loop roll. Volts in the battery, minus IR, minus Q over C. But this time, we're going to replace the current not with minus dQ dt, but a plus dQ dt. And the reason it's a plus is for the statement we had before, that the charge is going to increase on the capacitor. So we're going to put that in for I and change our equation up just a bit. So I have dQ over dt replaces the current in the resistor. We've got the same setup again, except one extra term, and this time I want to get all the Q's and dQ's together, and I want to get the dt to one side as well. So we're going to have to do a little bit of algebra here first. First thing I'm going to move is this term. And you can see I've got voltage minus Q over C on one side and dQR over dt. We want to write this all in terms of charge. So you can see that I have Q right here, but it's attached with a C for capacitance, and it's actually giving me voltage. To get Q all by itself, I've got to get rid of that C. So I'm actually going to take the entire quantity here and multiply everyone by the capacitance. That's going to eliminate this C, multiply my voltage by capacitance, and add an RC to this side of my equation. So it's going to get a little bit messier. So here's our setup. We've got voltage times capacitance. Voltage times capacitance, remember, is the charge in the capacitor in the end, minus Q, and on the other side I have dQ RC over dt. Remember, we had a e to the negative RC over dt, so I'm just going to move around some minus signs and make this plus, this minus, and make this minus. And then I'm going to do a little bit of algebra here. I want to get all the Q's and dQ's together, so technically this term is charge as well. Just through a little bit of algebra, we rearranged our equation now, and I've got dt over RC on one side, and I've got dQ over a quantity of Q minus voltage times capacitance, which again is Q. So that means we're going to have to integrate this, and when we integrate this, this is not going to be as nice as it was last time. So when I integrate for the capacitor, remember, had no charge in the beginning, and then will be fully charged, and we're going to do that from 0 time to any time t. Let's integrate the easy side first. Let's integrate dt. dt is going to give me t over RC, and then on the other side, what I'm going to be left with is a natural log of the Q. Now the Q is going to be between two locations. It's going to be putting in my two bounds. I'm going to get the natural log of Q minus EC, and then I'm going to subtract that from the natural log of just negative EC. What I did is I put in my bounds of Q and I put in my bounds of 0. And when I do that, remember, subtracting natural logs is really just dividing those two natural logs. So we've set it up this way, which again may not look much nicer, but we got to get rid of the natural log. So remember, we raised that to the E, and our natural log will disappear, which gives us e to the negative t over RC again. So we do have that exponential time constant again, like we had before. And then we want to solve for Q. So I'm going to multiply this negative EC over to one side. Done one more step in the algebra. I want to get Q in the end by itself, so I'm going to have to add over this charge and what you get in the end. So there's our final equation for the charge as the capacitor is gaining more charge. That's a really nasty equation. But remember, E times C, and the EMF, or the voltage times the capacitance, really is the final charge. And leave behind a 1 minus E to the minus T over RC. Remembering that RC is the time constant of our setup. So that's how you can find the charge at any moment of time as the capacitor gains the charge. This Q final here is the maximum charge of the capacitor, but now you're going to multiply by a 1 minus e to the minus t over RC. So instead of doing just e to the minus t over tau, we have this little 1 minus. So what does that actually do in terms of our equation? Well, in terms of our equation, instead of a decrease here, if I put in that t equals tau, or t equals RC, again, my time constant knocks out my time above, and I get e to the negative first. E to the negative first, remember, is 0.37, but I'm going to do 1 minus 0.37. After one time constant, my charge is 0.63 times the maximum charge on the capacitor. So I'm already at 63% of my final charge after one time constant. What if time equals 2 tau? Time equals 2 tau, remember, we are at now 13%. If you do e to the minus 2, but it's 1 minus 13%, so you're actually at about 87% of your final charge. So instead of an exponential decrease and loss in charge like we had last time, now we're increasing our charge until our capacitor is fully charged. You can see that exponential growth, and we gain the amount of charge at every single time constant. If you keep putting that in, you put in 4 or 5 time constants, eventually you'll be at the maximum charge of the capacitor. So we got charge. Well, how do we get current? Remember that current is the derivative of Q with respect to t. So it means I've got to take the derivative of this function up here. I've got to take the derivative of this function up here to get my charge. Taking the derivative of charge, what you end up getting is CE multiplied by negative 1 over RC, e to the minus t over RC. So doing the derivative gets you a little bit messier of an equation, but if you look, I've got capacitance up here and capacitance down here. So what I'm ending up getting here is that current ends up being V over R e to the minus t over RC. And remember that V over R is current. So our current equation actually is our initial current, e to the minus t over RC. So the current equation actually looks the same whether you're charging or discharging. Just remember that in this case, you're going to start off with max current and eventually die off to zero as the capacitor charges. Our current equation, again, it'll fall off at 37% at the first time constant. It'll be at 13% of the max current at the second time constant, and eventually by the fourth and fifth, you lose all your current. So if you've got your charge equation here and you wanted to actually know the voltage as time goes on, well, that's an easy thing to do. To get voltage, we just have to take Q and divide it by C. Q over C would give me the voltage at any moment in time. Dividing this by C would be the final voltage on the capacitor, multiplied by 1 e to the minus t over RC. So it would be just like the charge equation, since charge is proportional to voltage. More voltage on a capacitor, that means you have more charge on a capacitor. When we have the circuit here and we close the switch, what is originally going to happen at time equals 0 when the switch closes? Well, when the switch closes, current's going to come out of the battery. It must go across the 4 ohm resistor, but then it's going to hit this junction. And initially, the current's going to see two things. It's going to see an 8 ohm resistor, and it's going to see an uncharged capacitor. Well, an uncharged capacitor, remember, acts just like a wire. And so the chargers will say, you know what, it's going to be a lot easier if we go this way and go across the capacitor. So they actually skip and cut out the 8 ohm resistor. However, that part is cut short, because as the capacitor starts to grow and eventually reach the voltage that it holds, it'll shut down this entire circuit. And if it shuts down that entire side from C to D, what happens then is that the current will say, well, the capacitor's full, no charges can go across it anymore, so all the current then goes across the 8 ohm resistor. It's like this entire branch is now shut down. So now you've got an 8 and a 4 ohm resistor in series. Going through all those derivations is important, but they really are concerned with, they'll ask you right when the switch is closed, after a long time. What would happen now if the switch would reopen? Well, if the switch would reopen, well, the 4 ohm resistor would turn off. However, you have a charged capacitor. The capacitor would act like a battery for the 8 ohm resistor and send current around the loop, trying to maintain and keep the circuit going. So now that you know the voltage, the current, and the charge at any moment in time, what someone could ask you is, what is the energy transferred or dissipated by any of these components in a circuit? Remember the power equations. Power is equal to I times V, or it's equal to I squared R, or V squared over R. If you were asked, hey, what is the power delivered to a resistor at any moment in time, you would need the exact current at, say, this moment in time to tell you exactly how much power is delivered from the battery or to a resistor. If you want to know the energy stored in a capacitor at any moment in time, remember that the energy in a capacitor is 1/2 Q squared over C. And remember that Q also depends on time, so you have to find the Q at any moment t, and that will tell you how much energy has been delivered into the capacitor at any point. But that's just the energy stored in there. What about the rate at which the energy is stored in the capacitor? Well, to find the rate, I'd have to do du over dt. So if I want to pull out the constants there, that would be a 1/2 over 1 over c, leaving behind a q squared over a change in time. So if I take the derivative of q squared with respect to time, what you end up getting is 2q dq, and remember, we still have a 2c over dt. Q over c, remember, is voltage at any moment in time, and q over t ends up being the current at any moment in time. So that could be the power that a capacitor is receiving as time goes on, the rate at which energy is being poured into the capacitor. So we've got charging capacitors, we've got discharging capacitors. Know what's happening at any moment in time. We've got the equations for charging and discharging. But remember, they're going to ask you about a few locations on tests. They'll ask you right as the switch is thrown, after a long time, and what happens when the switch is open. Make sure you know what's going to happen in your circuit, whether you're going to charge or discharge, and what fully charged capacitors do to certain branches in your wires. So good luck. We'll talk next time.